In this video, I'm going to introduce different methods for sending information to the screen or to a file in the course of running a script or a function. We often want to do this so that the progress of an algorithm can be monitored. There are three basic methods for displaying text on the screen. First, remember that when a MATLAB command ends with a semicolon, the output is suppressed. On the other hand, if it ends with a comma or no punctuation, then the output is displayed. This mechanism can be used inside a script or function just as in the command window. As an example, I'm going to use my quad LHS function. Remember that this function applies Richardson extrapolation together with the left-hand rule to estimate a definite integral to a given tolerance. I'm going to show you a new version called quad LHS1, where I have removed a few semicolons. So here's the file. It looks exactly like quad LHS, except that if you look down here, I've removed the semicolons after the definition of N1 and I1 and N2 and I2. And then inside the loop, when I update N2 and I2, I've also removed the semicolons. So now if I were to run this, let's say I integrate the sine function from 0 to pi over 2, and I'll choose a tolerance of say 2 times 10 to the minus 3. There's the output that I see. Now I'm not very satisfied with this output. It takes 3 lines to display each variable, and in fact it would take even more if I were using format loose instead of format compact. And the output is not as easy to read as it could be. For these reasons, I don't usually produce my output by simply removing the semicolons at the end of the commands. Let's talk about the second mechanism for displaying output in MATLAB. It's the MATLAB disp command, short for display. It can be used to display a string or a variable or some combination of strings and variables. I'll illustrate the use of this command in the command window first. Let's say I have variables n1, which is an integer, and I1, which is a floating point number. Maybe n1 is 100, and I1 is an estimate of the integral that we were looking at. I could display the value of either variable without its name using the disp command. I can display a string to identify the value if I want, so I could display the string n colon and then display n1, or I could display LHS colon to indicate that this is the output of the LHS function, and then display I1. I would like to be able to display both the label and the value on the same line. We can do this with the disp command, but we have to know a little more about how MATLAB handles strings. MATLAB allows me to create a string by concatenating 2 other strings. Moreover, a string is regarded as an array of characters. Let me create a string. You notice here, as I said, that string is an array of characters. It's a 1 by 8 array, and the class is character. Here's another string. Now, since a string is an array of characters, I can concatenate 2 strings just by concatenating the 2 arrays, which I would do using the usual array notation. Now, we can use this ability to concatenate strings together with MATLAB's functions for converting numeric values to strings. First, let's look at the function int to string. It converts an integer value to a string. So int to string of 100 creates a string whose value is 100. Notice now ants is a 1 by 3 array of type character. We can then use this as follows. Let's display, I'll have a label which is n, and then int to string of n1. That's what I wanted to be able to do, display the label and the number on the same line. There's a similar function called num to string, which converts a floating point number to a string. There are 2 ways to control how num to string prints the value. First, the following version tells num to string how many significant digits to print. If I say num to string pi 6, then I'm printing 6 significant digits. Notice that the number of significant digits includes the digits to the left of the decimal point. Now you can ask for as many digits as you want, but the precision is always limited by IEEE double precision. So for instance, I could ask to print 20 digits of pi. However, I shouldn't trust the last 4 or 5 digits of the answer because IEEE double precision corresponds to about 16 decimal digits of precision. Now we can use num to string with display. So for instance, I could display the label LHS with num to string of I1. I can print more digits if I want. Now let's use what we've learned to revise our quad LHS function. Here's another version, quad LHS2, that displays the progress of the algorithm. Now I'm displaying the same information that I did before, but I think it's in a more concise and readable format. Let's look at the code. So here I do my first calculation. I set n1 equal to 20 and I compute the left-hand sum on 20 subintervals. Here's my first display command, similar to what I showed you before. Notice that I chose to display 5 significant digits. Now I do the second calculation. I double n, compute the left-hand sum again, and now I'm able to compute the error bound. So this display command is a little bit longer because in addition to n and the left-hand sum estimate, I display the error bound. Inside the loop, we have another display command, which is the same as the one we just saw. Here again is the output of those commands. I need to show you one bit of syntax. Here's the mechanism for continuing a line that's too long to display on one line. MATLAB is a line-oriented language. That means that each statement is assumed to end at the end of the line. If you have a statement that's too long to fit on one line, you put 3 dots at the end of the line and then continue it on to the next line. I mentioned earlier that there are 2 ways to control how disp displays a number, more precisely how num to string converts a floating point value to a string. We can pass as the second input a string containing the format in which we want the number printed. We can choose between ordinary and scientific notation and specify the number of digits to the right of the decimal point. Here are some examples. There I told num to string to display this in floating point format with 4 digits to the right of the decimal point. Here I use scientific notation with 4 digits to the right of the decimal point. Here are a couple more examples where I use 8 digits to the right of the decimal point instead of 4. Now we have much more control with the fprintf function, which is used to print text and numbers to a file or to the screen. Here's an example of the use of fprintf. First, let me define some variables so I have some values to print. And here's an fprintf statement. This statement is rather complicated, so let's look at it carefully. Fprintf takes 3 or more inputs. The first is a file ID, and 1 means the screen. So here's my first input, for which I used 1. We can also use fprintf to print to a file, and we're going to discuss this later. For now, though, we'll always use 1 as the first input to indicate that we're printing to the screen. The second input is a format string, which contains exactly what you want to appear, but with format identifiers in place of the values. %d means an integer value. So this says I want to print n colon and then an integer value. Notice that I made a slight mistake here because I'd really like a space between the colon and the integer value, so that's a little bit more what I intended. You might wonder why the d in %d. I think d originally stood for decimal. It might be more logical to use something like I for integer, but d is what's used. Now we've seen the %.5f before. This indicates that we're going to print a floating point number with 5 digits to the right of the decimal point. I use that twice here. We have to include the \n at the end of the statement if we want the displayed string to end with a new line. So here's what happens if we omit it. Notice that MATLAB printed the string that we wanted. However, there's no new line, so the MATLAB prompt, which normally would appear at the beginning of the next line, appears right there. Now remember, this would be called the format string. After the format string, we list the variables representing the numeric values that we want printed. Now notice in this statement we wanted an integer, a floating point value, and then another floating point value. So there are 3 variables, 3 values that we need to print, and they're listed in order at the end of the statement. We can use fprintf with just 2 inputs if we only want to print a string, like so. Although it's more complicated, fprintf allows more control over the output than does disp. Let's look at quad LHS2 again. Here's another version, quad LHS3, that displays the results in a neater format. Let's look at the code to see how I did this. Okay, so this code is the same as before, except I've changed the print statements. Here's my first fprintf statement. Now the key thing to look at here is the numeric format. So I now say instead of %d, %8d. This tells fprintf to print the integer in 8 columns, regardless of how many digits there are in the integer. So if we look back at the output, what I have here are 8 spaces with the integer value right justified. Notice I have to guess that 8 columns will be enough for this application. If the value of n ever got to the point where it needed 9 digits, then my output would not line up in neat columns as it does here. For the floating point value, I've also changed the format a little bit. First of all, I'm using exponential notation. I'm using the E format, because then the width of the displayed field is predictable. With the F format, I have the difficulty because I don't know in advance how many digits lie to the left of the decimal place. I could certainly write code to determine this, but then the code would be much more complicated. So let's make sure we understand this. I'm still indicating 5 digits to the right of the decimal point, but now I'm indicating a total field width of 12. Now how did I determine 12? Well, first of all, I have E followed by a sign followed by a 2-digit exponent, so that accounts for 4. I have 5 digits to the right of the decimal point, that makes a total of 9. I have the decimal point itself, which is 10. I have 1 digit to the left of the decimal point, that's 11. And then I need to leave room for a sign because the answer could be positive or negative, and that's how I came up with 12. The other fprintf statements are the same, except I'm adding in the error bound, which I display in the same way using %12.5e, and similarly here inside of the loop. So again, looking at the output, I have everything lined up in columns. It's very easy to read. And I use the flexibility of the fprintf statement to accomplish that. In the next video, I'll discuss other nuances of fprintf and also how to print the output to a file.